Hi everybody and welcome. In today's video we're going to be covering increasing and decreasing functions. So what you're going to hopefully get by the end of this video is a good idea of the definitions behind identifying intervals where a function is either increasing or decreasing. So what we're going to see is graphically this is one of the more straightforward things we're going to see, but unfortunately anything other than a graph, this can be reasonably confusing to calculate. So we're going to start off with some definitions. We're going to anchor everything that we are kind of going over right now in graphs, and hopefully if we have a really strong understanding of what the graphs of these look like, we'll be in pretty good shape to do calculations when we don't have graphs in front of us. So first things first, for increasing and decreasing functions. So a function is increasing in an interval from a to b. So imagine any number there. Say it's a is 1, b is 3, just from x equals 1 until x equals 3. So it's just telling us like a distance, a length. If for every single value in that interval where c is less than d, we see f of c is less than f of d. So all that this is saying is from some point on a number line, so let's say if we're like on the x-axis, if like c is here and d is here, we're just saying as long as we're moving from left to right, we should see that the function is also going up over that period of time. So that's kind of how we're measuring this, is specifically from the left to the right. We want the function to always be going up over that interval. So the trick here, though, is that sometimes you'll see a function might go up and then up. This wouldn't count because for the entire interval, every single step of the way does have to be increasing. So that's kind of the trick with these wordy definitions here, is that we're basically looking for a spot where the function is always, always, always going to be increasing over that entire time. Decreasing is just the opposite. Same kind of tricky vocab here, but same principle. So a function is decreasing in an interval from some values a to b if for all values in that interval where c is less than d, we're going to see this time that f of c is greater than f of d. And all that that's saying is the value immediately to your left this time is actually bigger than you. So if we draw this out from some interval from c until d, this time if you're at some value here, the value to your left is actually bigger. The value to your left is bigger. So it's going in basically opposite order. So like I said, looking at this on a graph, it's like, well, obviously that's decreasing, right? You can see it's going down. But the hard part is that definition of, if we're looking at this in words, okay, is it going down every step? Is it going down every step? Or the way that we really look at this is the value to your left, is it bigger? So kind of a backwards way to see it. The last one, a constant function. So a function is constant in an interval from a to b if for all values in that interval where, again, c is less than d. So that's just telling us when we go from left to right, from c to d, this time the function is actually equal. So if you're looking at your neighbor to the side, this time you are exactly the same value. So you're not increasing and you're also not decreasing. And those are the three different scenarios that we're going to see today. Most of our focus is spent on identifying, are we going up or are we going down? But just as important, we also need to know, is there a time or a place where we're doing neither of those things? We're just staying where we are exactly. So graphically here, this is going to be some of the value of what we do today. It's just being able to look at these things. The challenge, though, is you have to find that moment where things are at their absolute minimum or their local minimum, and that's going to help you determine, are we increasing or decreasing on these intervals? So looking at the graphs, the first thing that we want to do is always, always, always state any of those local mins or maxes, and then after that, only after that, are we able to start looking at things like increasing, decreasing, and constant. So if we look at the graph, a lot of these are already labeled for us. So like this point right here, they've already labeled this local min, the values for it. Typically, you're going to have to do that by plugging it into your graphing calculator or into an app like Desmos. So they're not going to necessarily give you these values. So again, a little local max here, and then another local min. And the reason why these local mins and maxes are so important and why we spent an entire unit on it before last week was because those are the points that tell us, those are the cutoff points that tell us the difference between when we're going up or we're going down, when we're increasing or when we're decreasing. So if we look at this function, I'll label in yellow every time we go down. So from left to right, these are the two intervals where we see decrease. And then in, let's do a different color, green, we'll say that that's when we go up. And you'll notice the exact instantaneous point where we change from yellow to green every single time is either a local min or a local max. So that's why in pre-calc we spend so much time on these silly things. We're like, oh, what does a local min matter for? Well, the real reason in pre-calc why we're focusing on these so much is that is the exact point that we can see the change in slope. We can see it changing from, a negative decreasing function to a positive increasing one. So looking at our first function here, the intervals where we're decreasing, we see it starts off at negative infinity, and that first local max is at negative 2, 2. So that is one. We'll have a union, and we'll start again at 0, and we'll go to 2.9. So all that I've done here is I've just pointed out in yellow the intervals on the x-axis. So this is our yellow interval. This is our second yellow interval. The next thing that we're going to have to do is identify increasing. So here, increasing, we're going to be looking at what's in green. So start off at, this time, negative 2.2, and we'll end at 0. A union, because there's another gap between our two green ones. And again, 2.9, and this time it just goes on forever. So again, to infinity. So we'll see, again, that these should form the entire function. If we put everything that we've identified together, there shouldn't be any exact spots where there's gaps, because we're either increasing, decreasing, or, you might notice this, we're staying constant. So this is a last final point, and this will be one of the spots in the course this year where I'll point out, if you are someone that wants to continue on to do calculus, so if you're ready to move on past pre-calc to calculus in the future, you're going to want to pay attention in particular to points where we stay constant. So constant points, if you're very, very good with interval notation, what you're going to realize here is that we've used parentheses. So when we get to that instantaneous local min or local max, that is not a bracket, which means that's not an included value in that interval. At exactly x equals negative 2.2, we are neither increasing nor decreasing. That's our point of change. We're changing in between those two things. So because we're neither increasing nor decreasing, that is the point actually where your function is exactly constant. So our constant values are x equals negative 2.2, x equals 0, and x equals 2.9. And the way that I understood this best, and again, like I said, this is extension. So if you are, if this is too much, that's okay. I'm not going to test you on this. But if you are interested in this, if you're taking a look at the slope of this line, what you're going to see is as we're kind of tracing this up, we're going down, we're going down, we're going down. We kind of start to smooth out, we're smoothing out, we're smoothing out. Slope's getting more shallow, more shallow, more shallow, more shallow. And then right when we get to that local min, at that point where we're no longer at a decreasing slope, and then we're right at 0. And then we start to change to go back up. And we see, okay, this is increasing, 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 and then we're following this line up, and then we're going up, we're going up, we're going up, we're going up, and then start to go back down. And then before we go back down, we have this instantaneous moment where we're at 0. So that's the power of these local mins and maxes, is another way, and this, when you kind of say it out loud, it makes more sense. When we're changing from negative to positive, there's a moment in between that change where we're 0. Well, that moment in between that change is where you can put the ruler flat on the function, and that just happens to be every single point where we have a local min or a local max. And those are going to be our constant points. So that is our challenge for today, is identifying and labeling those intervals, and you're going to see these in a variety of ways. So one thing that I do want to point out, and you'll see this on the worksheet quite a bit, right here, if you're not sure what this value is on the x-axis, if you're like, I don't really know what that local min or max is, don't stress about it, just label it. So if that's like, maybe that's negative 1.8, or going up to 10, and then here, maybe that's positive 1.8, who knows. -10. It's okay to guess. So if there is a picture given to you, as long as you label it, that is okay. So if they're just giving you a picture and it's not super clear exactly what it is, totally fine to guess and just label what you have. But a situation where it is not totally okay to guess is if they tell you to graph the function. So if you are specifically graphing this function, when you punch this into Desmos or into your TI calculator, you will in fact need to actually go through and get those exact values. So you'll need to click on this value right here in Desmos. You need to get that exact minimum. So no guessing when you are the one responsible for graphing it, okay? So what I'm gonna do, finishing up for our video today, is based off of what I've just labeled here, I'm gonna ask that you identify where is this function increasing, and I'll have you do that now. And I'll also have you identify where is this function decreasing. And I'll have you do that now. So increasing in green, and decreasing, actually, there's no gap. It's just one interval here, just straight in the middle. So looking through this, -infinity to -1.8. A gap will start up again at +1.8 and go to infinity. So again, just identifying what's in green. And we always are just looking at our axis here. So just going from here to here and from here to here. So everything that I just put in black, that is our x values where we are increasing. And then where we're decreasing is that gap that fills in the middle from -1.8 to +1.8. Be the answers there. Okay. So hopefully you did well on those two questions. Like I said for today, if you're looking at the actual images, this should be reasonably clear where things are physically going up or physically going down. The challenging part for today is just identifying when you are doing the graphing yourself or if you're going to calculate this out by hand, which we're not going to do too much of that today, but I'd say the big focus for you today is just making sure that you feel comfortable on Desmos plugging these in, making sure you feel comfortable if you're using your TI calculator plugging these in, and beyond that, also making sure that you feel comfortable with interval notation. It's really important to know, basically going from left to right, how to write out where we're increasing and where we're decreasing. All right, if you got questions, please let us know. As always, thanks so much for watching, everybody. Some good prep for this week, and looking forward to going over this in the classroom together soon.